Hello guys, welcome to this new episode today, number 40, and today we are going to talk about genetic algorithms applied to neural networks, and probably we also are going to take a look at our trained agent using SelfPlay. So let's get started. Okay guys, welcome again. So on Tuesday we had our evaluation session. So we evaluated one submission from one of our participants in the AI tournament that we recently launched with the RLZ, Reinforcement Learning Zurich. You find all info on our website under, you see here, DIAMBRA.artificialtwin.com, and then you can just go into AI tournament page. There you find all details as well as the leaderboard. And Alessio was here with us on Tuesday, 2 days ago, and we re-evaluated his agent. And in this case, the particular thing was that he told us about the technique he used to select, to perform a model search for his policy network. And so the architecture that seemed more promising were the one that we showed here. And so he was able to improve his performance with respect to the previous week ones, and this is of course good. But it was kind of very interesting to know which technique he applied in order to try to evaluate this different set of networks. And so we had the chance to talk about very briefly about genetic algorithms applied to this field. And since it was pretty interesting, we thought that it would be nice to see it a little bit into more detail. And so for this reason, today we have him already, connected with us in voice, and so welcome. Hi, Alessio. Guys. Hello. Nice to have you here. Hello. And so yeah, of course, today he is going to spend a few words about this technique, in particular genetic algorithms, in order to share with us main things about this approach in a very high level overview, not too technical, let me say, but technical enough in order to convey what's behind it. So main principles and how they can be applied genetic algorithms, evolutionary algorithms in general, are something that can be applied in general in optimization problems. Their application in deep learning in general, or neural nets, is very, very interesting. And so, hello, Lauder. Glad to have you here today with us again. And so, as usual, guys, don't hesitate to ask question in the chat, as you did on Tuesday. It was great interacting with you. And so I think that having said that, we can start talking about genetic algorithms. We do have a presentation prepared by Alessio. And so, yeah, here it is on my screen. Alessio, the floor is yours.
Thank you. Very nice introduction, Alessandro. So yeah, as you said last time, you have seen my agent trained using genetic algorithm, and so the idea behind genetic algorithms is that we want to mimic Darwinian evolution. We will not talk too much about the details, but I just want to go through like the main concepts of GA.
Yeah.
So we can go to the next slide, and here you can see an example of how GA has been applied in the engineering field. This is a special type of antenna that was developed by NASA in 2006, and this shape was found by an evolutionary algorithm. It was found by a genetic algorithm, and this shape, this pattern, is like one of the best pattern to create radiation, so to propagate radio waves in an efficient manner. So it's really interesting. We can use this kind of algorithms to find really complicated stuff for complex problems. So the idea is to draw inspiration from evolution and try to mimic evolution to solve very hard objectives. So in the next slide, we have what are the main steps, how genetic algorithms work. As I said, they are inspired by the process of evolution, by natural selection. The idea is that we start with a population of candidates. In our case, we have a lot of neural networks. So we have like 100 neural networks, and this is our population. What we do after we evaluate each network, we select which network is the best one, and amongst the best networks, we mix them together. This is called reproduction or crossover, and also we do mutation. Like in viruses, like COVID, we also have mutation, and the idea of mutation is similar to exploration. In reinforcement learning, we do exploration using epsilon greedy strategy, or UCB strategies, or many other strategies. The idea is the same here. We want to perform mutation in order to explore. We get a new population and we keep going. That's the idea behind.
Okay, so I do have a question. I think you are going to, at least briefly describe. I'm wondering. I'm slightly familiar with these approaches, and reproduction as well as mutation are usually very specific to the type of variables you have to deal with. And so I'm really curious. I believe you are going to share with us a few details about how to do this kind of stuff with neural nets, right?
Yeah, exactly.
Okay, great. So, okay.
Yeah, in the next slide, we can see a lot of turtles. The idea is that we start with a population that is random enough. We want our initial population to be very large and have a lot of variety, because each network, each individual, or I also write candidate, each candidate needs to be different from the others in order to have like a good exploration. Unfortunately, the space of parameters in neural network is very large, but we can appeal to the fact that for over-parameterized neural networks, there are a lot of minimas, there are a lot of flat regions in the space of parameters that are good enough for the problems we want to solve. And so it's quite likely that we end up in a region that is like kind of nice for us or good.
Okay.
So yeah, the idea is we start with a large population that is random enough. And the next step, so it's to evaluate the population. And to evaluate the population, you need a criteria. The problem is sometimes you have to deal with stochastic problems where you have some randomness, and so you need a good criteria. You might want to evaluate what is the average reward you get, or you want to maybe assess what is the minimum reward. It depends also on the application. Sometimes you want to be very strict, other times you don't need to be so strict, or maybe the problem is deterministic, so you don't need to compute an average. But here the idea is you want to evaluate each turtle. You want to evaluate each network, how good the network is. So you use the best networks to do the crossover and the mutation.
So, and I believe that in some sense this should be related with what in RL, I mean, with what we call the reward, right, of our environment. It should related to it. Should be related
exactly.
to it.
In my case, last Tuesday, I was evaluating the total reward of the agent, but I was evaluating the total reward up to the last stage, because there is the problem that if in the last stage you get a lot of negative reward, this might affect like what is the score of the agent. Sometimes you reach a really good high stage, maybe you reach stage 6 or 7, but maybe because of the last stage you get -4, and maybe the reward was not already that great, but still the agent managed to reach level 7, stage 7, so it must mean something. It cannot be like a coincidence. But yeah, anyway, in my case I evaluated total reward and
nice.
And yeah, so the next step after you do this evaluation is to select. How do you do selection? It depends on you. You should define some kind of threshold. I want like the 10% of the best networks to stay alive, and the remaining 90% I discard all of them.
Okay.
So this 10% is also called elite group. You see there is a turtle with a crown. That's like the best network. And this represents the leader. And the other turtle is also a good turtle. It's a good network, but it's not the best one. The one with the crown is the best one. And this is very important. It's very important that we keep the best networks alive and we don't lose them. Otherwise, maybe you lose track of what is a good network. And this is called elite group. Best candidates move on to the next epoch without any change. That's the idea. And from this elite group, you also generate new offsprings. You do mutation and you do crossover.
Okay.
So it's really important, this group. The remaining turtles, the remaining networks, you just discard them. You don't care too much about them. And since you discard these networks, it's very important that your elite group is large enough, but not too large, because otherwise you cannot do like reproduction. Obviously, you cannot do reproduction if you have like only 2 networks.
Of course.
I mean, you do reproduction between 2 pairs of network, you can get only 1 additional network.
Okay.
And if you perform too much reproduction on 2 similar networks, it's not going to work well. But we will see it now.
So if I got it correctly, you use the population in your example that you showed us here. You used 100 networks and as a population, so the total number of networks was for the population was 100, and then you selected like 10%. You said
Yeah, exactly.
Okay,
Exactly.
so 10 networks were selected at each step, and then you created the crossover or reproduction starting with these 10 networks, right?
Yeah, exactly. So I picked the 10 best networks.
Okay.
And these networks, they move on to the next epoch without any change.
Okay.
And then I use these 10 networks also to
Okay.
perform reproduction and mutation.
Okay.
So the
So
remaining,
additional 90 networks from those 10. So those 10 were kept the very
exactly.
same, and then additional 90 were basically created.
Yeah.
Okay.
And most
Okay.
likely the remaining, the new 90 networks, maybe they are really bad. So it's important to keep also the 10 networks that were good from the previous
Okay.
stage in order not to lose them.
Okay. Of course. Very clear.
Yeah. Yeah, so the next two steps are reproduction and mutation. So in step 4, we have reproduction. And the idea is to mix together the networks. And there are several ways to do it. I've never, there are not so many papers about this. So I actually came up with my own ideas how to do it. The idea is you take two networks.
Oh,
You have
nice.
network A and B. You have two turtles. And both networks, they have the same structure. The idea
Yes.
is to take like n layers from one network, like the first n layers, and we pick the remaining layers from the second network. So imagine you have a network with 4 layers. You can pick the first 2 layers from network A and the last 2 layers from network B, and you mix them together in this way. In my
I believe you're talking about weights, right? So you use weights for one network and mix with weights or the other, right? We are talking about architecture.
Weights.
Okay, weights. Oh, okay, perfect. Okay.
You can also do it with architectures. It's
Okay.
Doable. It's not
Okay.
impossible. But the problem with that is you need a lot of computational power to try different architectures, obviously.
Okay, I see. Okay.
And I call this technique layer crossover, because you do crossover, you do reproduction between the layers of the networks. So you exchange the parameters of one layer from one network to the other. So
okay. And have you also experimented with only with single point crossover, or maybe or also with a different number of crossover points?
I only tried single point crossover. So the point at which you perform crossover is chosen at random.
Random. Okay, perfect.
Obviously.
Okay.
And but yeah, when we can give a look to the library later on, and you can see that it's really easy to add new crossover strategies.
Okay.
Basically, I implemented my library so that you can add your own strategies in a very easy way. So
okay, nice.
We can give a look later.
Okay, perfect.
And finally, we have mutation in step 5. And you can also perform mutation before crossover. It's not like there is not a fixed order. The idea of mutation is, as I said before, is that you want to add some sort of noise to the parameters. So we are doing exploration in the parameter space. We are not doing exploration at the action space, like in reinforcement learning, but we do exploration in the parameter space of the network. And the thing is, you can add any kind of noise. You can use Gaussian noise, you can use uniform noise, you can use Laplacian noise. In general, Gaussian or uniform is okay. And in the library, you can also add noise, a different kind of noise for each different layer. So the noise can be different from layer to layer. And it's really important, for example, to have you can have maybe a noise with larger amplitude at the bottom layers and the noise with smaller amplitude at the output layer. Because, maybe if you change too much the parameters at the output might change too much, too drastically.
Okay.
Instead, if you increase the exploration rate at the bottom layers, so the first layers, it's unlikely that the output will change much, since these layers are just at the beginning of the network.
Okay. Okay. So there's should be a lower influence when you change those layers down at near to the output part. Okay. Very interesting.
In principle, this is similar to the idea of using different learning rates for each layer. So some people they try to use different learning rates in each layer. So for example, you can use higher learning rates at the first layers, because at the first layers they receive a gradient that is usually very small.
Yeah.
So the idea is maybe we can increase the learning rate in the first layers in order to increase training.
Okay, so we do have a question from Lauder in the audience. He's asking how is initialization performed in the very first step when creating the population. I think.
In the library, I use a Gaussian noise. So basically, I just sample a network from a Gaussian distribution.
Okay.
But you can implement your own way to initialize the population. You can also use uniform noise, or maybe you have some kind of prior knowledge you can exploit to design the initial population.
Oh, nice. So do you think that this could be something that can be applied, for example, also when you have like a network trained with, for example, imitation learning or something like that?
You mean you want to copy another network?
No, I mean, let's suppose that you have like a reference implementation, a reference model that has been trained using imitation learning. So on, to behavioral cloning, to clone human behavior on a game, for example. And so you may start from there instead of maybe adding random noise to that one to create the initial population.
Yeah, exactly.
Okay.
There is also a way to load an initial population if you want.
Oh, okay. Okay. So it could be possible, for example, to load, I'm just wondering, like a population of different networks with different behavioral cloning coming from different players, for example. So in order to mix players, player styles.
Yeah.
Okay.
Yes, exactly.
Nice.
During last week, I had to train my agent several times. And also, I use my computer also for different things, so I cannot train all the time. And every time I start training, I just load the previous population at the last step.
Okay, okay. So you basically dumped the point at which you were arrived, and then you restarted from that point on, right?
Yes, exactly.
Okay, nice. Okay, very useful. This is a handy thing for a library. So being able to stop and restart, very useful, of course.
Yeah, and the library is really easy to use. We can give a look
later, of course. Yeah.
So in the next slide, we have the library. I called it NNGA, which stands for Neural Network Genetic Algorithm Library. It's pretty new. I use it also for other projects where I need to use some kind of, I cannot compute gradients, or it's quite hard to do optimization. So yeah, I started this library because it's quite useful actually, and I use it in many projects. And
nice.
Here
this one is publicly available, right? You also shared it on our Discord server, if I remember correctly.
Yeah. It's on Discord. You can find on my GitHub. I keep working on it, so many updates will come in the future. I also want to make it like distributed, so you can use it on different computers.
Nice.
And that's really nice, I think.
Very interesting. Very interesting. Yes.
So in the next slide, we have a simple example of how to start. I hope it's clear. You can see well. So here on the left, you see how you can start using the library. You have the import, you can you import the Gaussian initialization strategy, Gaussian mutation strategy, layer-based crossover strategy, and population parameters. And in the beginning, I define what is the network. I define what is the network structure. I called make network, and make network creates a network with only one hidden layer in this case. This is a network with 4 inputs, a hidden layer with 64 neurons, and an output with just 2 units. So I create the network, and I tell the idea is that you need to tell the library what is the network structure. So here I have network structure on the left. Network structure is a list of shapes where each element of this list is the shape of each layer. So like what is the dimension of the layer, how many neurons, what is the input size and the output size specifically.
Yeah.
So, and we use this network structure in the library, otherwise the library doesn't know what is the structure of the network. Then I define what is the population size. In this case, we have 100 elements. I define what is the mutation strategy. In this case, I use Gaussian mutation strategy. Gaussian mutation strategy is you just add the Gaussian noise to the parameters of the network with zero mean. And in this case, we have a standard deviation of 0.1. But you can also define the amplitude of the noise. You can define the standard deviation for each layer. So each layer can have a different noise. You just change the standard deviation there in Gaussian mutation strategy, and you write a list of numbers instead, a number for each layer.
Okay, nice.
We have layer-based crossover strategy. Layer-based crossover strategy implements the crossover strategy I was talking before about, the one where you choose where you choose n layers from the father and the remaining layers from the mother. And finally, we have Gaussian initialization strategy. Gaussian initialization strategy tells you how the initial population is sampled, how is it created. In this case, we sample networks from a Gaussian distribution with zero mean and standard deviation 1.
Okay. Nice.
So this is all you need to do to define the properties of your GA algorithm.
So everything is here, I see. Basically, it reflects the circle describing how to perform these kind of things. So initializing your population, then you are going to select the best one, then you perform crossover, mutation, and that's it. You get back to the first point, and then you start over again. So every element is imported right here and is configured here, having the network. You have to share the network structure, as you said, because you have to keep that in mind. Every single strategy like mutation and crossover needs to know the network structure in order to perform it appropriately. And it's pretty clear. I think it's the first time I'm seeing this one, and it's pretty intuitive to how understanding how it works. So very clear.
Exactly. And if we go to the next slide, we have a short description of what I just said. So
perfect.
We have the Gaussian mutation. We just add Gaussian noise to the parameters of the network. The layer-based crossover, we select the first m layers from the father and the remaining from the mother. And finally, initialization strategy is how we select the initial population.
Okay. Yeah, very clear. I totally agree with you, Lander. It's, kind of very simple to match what we are doing here with the general approach. So the high level overview of how this type of methods work. So for now, it's I must say it's very one-to-one correspondence, very clear to interpret. So
finally, we get to this last slide, and first we define what are the parameters of GA, and now we pass these parameters to the library. So here on the right, you see an NGA. An NGA is the main class of the library. I tell the library I want to run GA for 100 epochs. So in each epoch, I evaluate my population. I do evaluation, I do selection, I do reproduction, I do mutation, and then I move on to the next epoch. Fitness function is the function you use to do evaluation. It can be anything. In DIAMBRA, I run simply, if I remember correctly, for episodes. So fitness, it's a function that calls that runs 4 episodes in DIAMBRA and returns the total reward. Then we have population parameters, mutation strategy, initialization strategy, and crossover strategy, which we already spoke about before. And then we also have, you can define the number of cores to use non-processors.
Oh, nice. Yeah.
And you can also use callbacks in case you want to use them. And you finally you call the library by writing ga.run at the end.
Nice. I do have a question. I'm looking for it, but I don't see it. Where do you specify the threshold for selection? I mean, you talked about 10%. Is it something that you have to specify somewhere inside the selection strategy?
Very, very good question. Thank you for this. So population parameters, it's an object with different parameters. Here you see only population size equal to 100.
Oh, okay.
But in this class, you can also define what is the size of the best group. So by default, it's 10%.
Okay, so it's a default value of the class population parameters.
You can change it, but maybe we can give a look to the library so you can see.
Of course. Okay, so let me say, first of all, thank you for the presentation. It was, crystal clear to me. Let me just go to our Discord server. In the tech discussion, we do have your library shared, and this is it. So if you want, you can guide me through this code. A very quick question. I saw you updated it like 39 minutes ago. I must say it's super up to date, this library. So do you want me to, I do already have it on my PC. Do you want me to download it to run a couple of examples, or do you think I can use that one? The one I already have.
You can use the one you already have.
Oh, okay, perfect.
It's not a problem.
Well, nice. So
you can go to NNGA and go to population parameters.
Okay, I'm opening it. Okay, I see. Oh, okay. So in the initialization method, we do have population size that it has not a default value. I see here.
Yeah.
And then we do have a elite fraction that is 0.1. Here, I believe it's the 10% you were mentioning before, right?
Exactly. 10% is that group, the best group.
Okay. Nice. Okay, so
and then we have also other parameters like offsprings from elite leader fraction. This 10% is basically the number of networks we generate from the leader, so from the best network.
Oh, the very best one.
So yeah, exactly. So 10% of the networks will be generated from the best network. Then we have offsprings from elite group. This is 20%, and we generate 20% of new networks from the overall best group of networks.
Okay.
And this is just mutation. So we do only mutation here. Then we have crossover fraction, which is 50%. Basically, the 50% of the new networks will be generated according to the crossover strategy you use.
Okay.
And finally, we have random offspring fraction. This is 10%. So 10% of the new networks will be randomly generated totally at random without using the group of best networks.
Okay.
And finally, there is also this crossover mutation probability, which is the probability of mutating a network generated from crossover.
Okay. I think it's pretty clear. Very, very nice. You know, you do have a lot of things to play around with, I see. And so, yes.
And I just want to show you another thing before maybe we go to the examples, to show you how flexible the library is. So if you go, for example, to Mutation Strategy.
Yeah, I'll just open it.
So in this file, we have different strategies. In this case, just two strategies. We have a Gaussian mutation strategy and uniform mutation strategy. And the code is really easy. You can add your own mutation strategy. You can add your own crossover strategy, and it's really easy. What you need to do is to define a new class, define a function mutate. This function receives a network. And what you do, you just return a new network where in each layer you add the noise you want. So for example, in uniform mutation strategy, in each layer, I add noise drawn from a uniform distribution. And you see, I use exploration noise as amplitude for the noise.
Okay.
And multiply the noise by this exploration noise.
And the exploration noise is in the mother class, let me say, in mutation stuff. So the higher class. Okay, yes.
Exploration noise, you define it in your code where it's a parameters. It was 0.1 in the example.
Yeah. Yeah. Okay. Perfect. It's very clear. So here we have the normal distribution for Gaussian and a uniform one for uniform mutation strategy. So if you want to add something different, you can just replicate this one, change the name, and tweak the mutate function method inside it. Okay, it's very clear, I think. Okay.
Yeah, and it's the same in the crossover strategy also.
Yeah, I was going to ask that if we could take a look at the crossover strategy. So this is the general one, I believe, and this is the layer-based crossover strategy, the one that you used in that example. Yeah. Yeah,
layer-based crossover strategy is the one I use the most. So you see, there is this crossover function. This crossover takes as input three networks.
Three networks.
Yeah, because in some cases you want to do crossover between three networks. But in most cases, you only use two. In this case, I only use two. And you see, I choose at random a crossover point.
Yes.
And the minimum, it's 1, because layer 1.
Yes.
And you see, I return layers from the father until the crossover point, and then I choose layers from the mother, from Y, after the crossover point.
Okay, so X and Y are the two lists in this case used. Yes.
Yeah, exactly.
Nice.
So you see, it's very simple. You can implement your own strategy. You can implement a double point crossover very easily. It's
yes.
It's very simple.
So let me think. I'm trying to remember all times when I studied this kind of evolutionary algorithms that are kind of very interesting. I remember about the selection, the one that you are performing, correct me if I'm wrong. So you are basically evaluating every single network and you're defining that threshold of 10, right?
Yeah.
10%, I mean.
Yeah.
You are selecting those best 10 and then you do what you need to do with mutation and crossover. I remember that at least one other method that was like, it was called like a tournament, just to keep in the same dueling mood as in DIAMBRA. I believe it worked something like you keep couples of networks, in this case of individuals from the population. You make them fight one against the other in terms of you evaluate them, and the one with the best the one with the best performance fitness measure will be put in the elite group. The other one will go in the discard group, but you evaluate this couple twice at least in order to give the chance to the other one to win at least one time. And so you basically at the end have number of wins that can be 2 for 1, 2 for individual A, 2 for individual B, or 1-1. And if I remember correctly, like this technique was aiming at the elite group was the one composed by individuals with 2 wins. Then there was individual with 2 losing 2 times were discarded completely, and individuals with 1-1, just winning one out of the 2 matches, let me say, they were like kind of you gave them a chance in some way, like sampling from this group in some way. And so that was called tournament, I believe, and was a different way of performing selection from the population, if I remember correctly. So I remember that this is kind of another point in this process, in this round process, in which you can of course sit down, take think about how nature works, and try to mimic this kind of the nature in these kind of things. And this is really I think inspiring and rewarding, trying to identify different ways in which nature allows you to compare performances in terms of adaptation to the environment in some sense.
Yeah, it's very interesting. Actually, it's something I want to implement. But I want to implement it in a way that it's modular. You can choose your own selection strategy.
Of course.
So this is a feature you will see maybe in the future.
Okay, nice. Very, very nice. Okay, so I think that we already saw a lot of things, and we can test it in RL. I believe that you in your repository, you do have examples, as you can see here.
I have two examples of reinforcement learning and one of multi-class classification.
Nice. So you see here, and the two examples of reinforcement learning. One is, two very famous. One is Cartpole, and the other one is Lunar Lander. And maybe I will, it's kind of nice. The Lunar Lander is also very famous. Would you, like to describe it very quickly, Alessio, if you don't mind?
Yeah. So in the Lunar Lander example, we have a rocket. And we need to land the rocket exactly between 2 flags.
Yeah.
So it's not an easy environment in the beginning for new people, for someone that doesn't know very well RL. Actually, it's the same environment we use in our RL course at KTH, and students struggle usually to solve it. So it's not easy, but you can reach a decent reward with GA. So maybe people and students can use GA to find a good network, and then start with this network and apply RL after to improve it.
So what are the, could you maybe briefly mention the observation space and the action spaces? I believe it's a continuous control problem. Am I wrong?
Yeah, the state space is 8-dimensional. Of these 8 dimensions, 6 are continuous and 2 are discrete, if I remember correctly. So the state space is like x and y position, x and y velocity, angular speed, angular position. And you also have the observation if you have landed on the left leg or the right leg.
Okay.
And the action space, in this case, if I remember correctly, is discrete. We have 4 actions, if I remember correctly. You can fire left, right, or you can fire down, or don't do anything.
Okay, it's very clear. Perfect. So yeah, I heard, I never experimented it, but I remember saying that is not super easy, this environment. So I totally agree with you. It's kind of a nice example in order to give the sense of what RL this task is like when performed by a random agent. Let me execute. I think I do have an example to show a random the performance of a random agent on this specific environment. So let me run it right away. Okay, so you see here, you will see this is a random agent. You see that is basically falling down in very different ways, and so very bad performance. At the end, we will have an average score for each for these 10 episodes. As you can see here, the average is minus 547 in this case. Actually, I believe that for this number is not, I think is not the average, but is the that modification you had of the fitness function, Alessio. If you want to spend a few words about it.
It's a lower bound on the mean. Basically, what I return is the lower bound of the confidence of the mean. So
of
with
course.
95%, the mean will be above that value.
Okay, so basically you are subtracting from the mean like 2 sigmas, right? From the mean in this case.
Yeah, I subtract a confidence term that is proportional to 2 times the standard deviation.
Yes, perfect. So yeah, that was the meaning of that number. Now I do, if you took a look at this one, you see here in the main function how to execute everything, how to use this example. You find this file, I added just a few modifications, but you find it on the web. And so in Alessio's repository, you see here network structure, you create the network here, network structure, then you have, let me just zoom in a little bit, you have the population, basically everything we already talked about in the presentation. You see the very first, the very same thing. And then you initialize the method, you run the method here for the number of epochs you prescribe, and then at the end you are visualizing the final network, the one that obtained, at which your RL converged. So since it takes a while to reach a good solution, I already run it, and I should be able to show you the evaluation of one converged network. So let me try to see Lunar Lander eval. Okay, let's see how it goes, this one. And so as you see here, yeah, it's way more gentle in how to handle these controls you see here. And we will see at the end also the performance. Remember, minus 500 was the other one. You see here how with this example we were able to obtain this agent here that is performing continuous control in order to obtain these performances. And you see here we are almost at half our number of total episodes. We are able to land every time in the good way, and also near to flags. I believe that a good bonus score is awarded for landing there, right, Alessio? I'm not sure about it.
Yeah.
Okay. And
but if you look at the last change I made in the repo right now, if you try it, I think it can reach a very good score in 15 minutes maybe.
Oh, nice.
Now it was 167.
Yeah, you see here.
Cool.
Yeah. And again, guys, here is genetic algorithms at work, you know. So the very things that we discussed with Alessio in these slides. Super cool, very, very, very interesting. Thank you very much, Alessio. It was really a nice presentation, and a very complete also example here to, you know, convey the power of this approach. Let me tell you that in some sense we are treating, if with machine learning in general, we are trying to let data substitute analytical thinking in terms of trying to find a good solution for a problem. So we are basically trying to find out the model using data instead of trying to model the world. In this case, we are even abstracting more, because we don't even think about how to train this stuff. I mean, how to handle back propagation. We are not thinking about that even, in even more. The approach is like black boxing everything, and we are just I mean, between quotes, we are just applying, trying to give these black boxes as inputs to the nature selection way to perform evolution in some sense. And so
which is another black box in a sense.
Yes, exactly. And so it's, of course, as anyone can infer here, the computational power required is maybe even greater than, for example, DeepRL in general, as a general rule, let me say. But this is something that can be, of course, very, very clear. At the same time, you see, you are not even, entering into details about the network, taking care of gradients. You are not doing all those things. You are just let your networks evolve from an initial random population and just based on their fitness function. Very cool.
And you can use like more smart mutation and crossover strategy. What I use is really simple. It's the most simple things you can do, really.
Yes. Yeah, and even though you see they are able to produce very good optimal solutions for these problems. Okay, very, very nice. Perfect. I believe, it was really interesting. Again, thank you, Alessio. I'm really happy we had the chance to share these things together. And, I would love for you to stay with us here, because now if I'm able to make everything quickly available, we should be able to evaluate a new version of the agent that is undergoing SelfPlay. So an evolution from the previous model we had that we saw last week. So
you restarted training.
Last week we reached, I can easily show the situation, I believe, here. So the model started from scratch. After 1 week, it reached 6.5 million steps of training, and it was not bad. So around 3.4 more or less as a total cumulative reward average. Then after another week of training, we found out like it was just able to play with bus because it was spamming with kicks. That seems to be a good policy only for bus. And so that was this model, 13 million steps model. So what I did was I put this model 13 million together with 6.5 million in the list of model from where to sample, so previous model from where to sample, and I restarted training from this point here. So from 6.5 million steps trained agent, so I went back 1 week and restarted from there, and I arrived at this point here. So 13 million again, but now this is should be a different version of with respect to the previous one. So this should be what we are going to see now. I'm really curious because now this kind of experiments are starting to get really various in terms of how we arrived at this point.
Yeah,
and
it's
so
really interesting to see what's going to be the result. But
exactly.
did you change? Have you changed any parameters, or you kept the same parameters?
Well, I think that one thing that I changed was I kept learning rate and clipping ratio. Their schedule, it was more or less, instead of decreasing them, they were almost constant. And so yeah, this is I believe that was the main change I made. I just I think, okay, I did so many things I don't remember. Yeah, that was one thing. So changing learning ratio, how it was decreasing, so basically keeping it constant, and that was one thing, of course. And the other important change I made is adding that 13 million steps agent into the list of opponents from where to sample. Yeah, I think just these two. So these two should be the only changes that I made. So yeah, let me see if okay, now self-play learning. I just have to be sure everything is aligned here. We are using discrete action space with the attack buttons combination, so an action space with the size of 16. Okay, we are not using stage, of course. Everything should be okay. PPO, I do have to yeah, this one is the one that I have to change, is 13 million. It's underscore B, and this is stands for BIS, and this should be ready to be run. Okay, let's keep also here 7 episodes as we did in the previous times. Okay, I believe everything should be okay now. Yes, hopefully. Otherwise, we are pretty used to debug in live, so that won't be a problem. Let's see if it goes as expected. Okay, we are ready to evaluate this new agent undergoing self-play. Let's see if everything starts. Okay, I do have to do one thing here. So auto 8 panel. Okay, let's see. We are loading everything. Oh, remember that the one at 6.5 million training steps, that agent was lucky enough when playing with Rido, he was able to complete the game. Yeah, so weird, but that was a very, very lucky run. So hopefully, it was at least a point in which the situation was not compromised, while that checkpoint at 13 million steps we saw last time, yeah, that was looking very, very compromised in terms of possibility to recover from that situation. Okay, we are using GenFu. Let's see if everything goes well, because okay, now it seems okay, perfect, it is working. Just a sec. Perfect. So let's see if no, it seems we are not using just kick anymore, so at least way better than the previous one in this regard, at least. Let's see. Okay, so GenFu, I believe, is not a super powerful character, so facing Ayane is, even if at the very first stage, shouldn't be too easy, but we are performing not bad, I think. So self-play is kind of at least something better than the previous run. Nice. This one was almost a perfect. Not bad. Okay. Especially if compared with the previous situation we had last time. Okay, let's see GenFu.
Yeah, it's much better than the last one.
Yes.
Okay.
Yes. Exactly. Totally agree. Also because this old man is not so powerful. It is, you know, it could be very powerful because it has a lot of counter moves, but it's so hard to learn those things. Yeah, here you see here these continuous catches by Byman are always a problem, even though now we should be able to exit from these catches because we have the possibility to press multiple attack buttons combination all together. I'm not sure why this is not happening, at least not so often as one should expect. You see these kind of continuous catches are really a problem with Byman. Okay,
you're using PPO, right?
Yes, exactly.
Yeah, I think it's really hard for PPO to explore. It's on policy method, so usually they have a hard time exploring the strategies.
Yeah, you know, you are raising a very, very nice point. I started with PPO and with you know, facing the game, it was able. Oh, now we are using Raido. This can be interesting. Well, playing against the game, you know, it was able to perform very well. But with self-play, I totally agree with you. I do had in mind to at some point in the near future to experiment with different approaches, like using replay buffer memory with prioritize sampling from there in order to use off policy methods, and that could be definitely something to explore. It could be very, very interesting. And so maybe also sample efficiency could be improved easily. Yeah, it's something to look into, definitely. So we'll see. The only problem is here that there are so many interesting things, and you just showed one today about GA. I cannot, you know, the idea after watching your presentation, but also your code, your library, it was so clear how to use it, so clean, let me say also so controllable in some sense, meaning that there are no problems, hidden problems, things that you can miss. It's all there in front of your eyes, that it could be a very good thing to test extensively in some sense with the right amount of computing power. So, you know, there are so many interesting things in this context and this field that it would be, it's not simple to test everything that could be interesting. So yeah, that's the main problem here. Without, you know, considering the fact that, just let me, I want to, decrease the volume of the game. You know, we are playing with this game now, but we do already have 4 of them, you know, 3 additional games. And, you know, there are so many things to test. Just to give you another idea, here we are using just convolutional networks and fully connected ones. But of course, one thing that I would love to try is also recurrent networks. That is something that you are already doing, Alessio. And this is also another very, very nice thing to test. And so, you know, a lot of different options. We are working to add a ton more games. And this is something that is gonna be so exciting. And also, you know, this is just the very first tournament. We are gonna provide.
This is a PlayStation 1 game.
You know, this is I'm not sure. I believe so. The thing, you know, we are using the very simple and the same interface that is the MAME, that is called that is the one that provides you the arcade. Those, you know, games that you were able to play in cabinets, in bars, and so you know, yeah, and so
during the summer.
Exactly. And so, you know, that is one thing. The fact that soon there are gonna be additional games here, and also we are working, this is just the very first tournament, but soon we are gonna provide you all with a very, very fun, I don't want to, you know, spoil anything, but a very, very fun environment to get involved at a very deep level in this kind of you know, universe, the RL universe, taking your own pace to experiment. And so, you know, hopefully, and I'm saying this just because, you know, there are so many things to test, but hopefully soon we will have you all from the community that now are starting to get familiar with the environment, performing different tests, exploring different options and strategies to, you know, also that can also be shown here. And this is, of course, as you see, we just, you know, had the chance, thanks to you know, the work Alessio is doing every day in his own job. We had the chance to get familiar with GA in neural nets, and this is the power of being a community, a passionate community about RL. So you know, we would be able to explore different direction, everyone with his own preferred direction, and that is what we are really looking for, because it will allow to share here with everyone different angles to approach this kind of problem. So really looking forward to it.
Yeah,
so
that's incredibly exciting.
Yeah, I totally agree with you, and you know, also having the chance to watching, like in this case, what you did is very, very interesting.
You were speaking of new games, and
yes,
I don't know if you remember, but some years ago, a bunch of people, they played Pokemon on Twitch, and people were controlling the game from the chat. Have you?
Oh,
do you remember it?
No, I didn't know that. The idea of
it was really crazy. It was crazy, and I remember I was a master student, and I couldn't study for the exams because I was watching Twitch. I was watching these people playing Pokemon from the chat, and it was incredible. And it would be incredible to train an agent to play Pokemon. Actually, I think.
For example, yes, of course. You know,
it would be crazy.
Yeah, I totally agree with you, and you know. Let me say this one again. I don't want to spoil anything, but as you see here, we are focusing on a specific type of games, and this is for a couple of reasons. But of course, you know, this is not like a limit. This is definitely not a hard limit, and we do have in our plans things that are going to blow. I should say every machine learning scientist, engineer, or researcher his mind away, because the idea here is to provide really environments that are so amazing. The idea to play them with RL is just for now incredible. So I really. Everything is on our plans. We just need the time, right amount of time, step by step. We are gonna be there, and so you know, it's just everything is just starting here. But I make sure that everything will be here and will be on our repository, of course, on our environment. So it will be crazy, and yeah, it's just.
I look forward to the day where we see an agent training live on Twitch 24/7.
Yeah, that's another cool thing, you know. Yeah, that's also something definitely cool, because you can, you know, get back like in 2 days or in 1 week and see what's the you know, improvement he made. I remember that OpenAI 5 was talking about how they evaluated at first how SelfPlay was performing on their OpenAI 5 for playing Dota 2. They said like they were coming back every week in order to monitor and take a look at improvements, and they say that like the very first week they were watching, okay, remember they had a great computational power available, but the very first week they were just watching agent going around the environment, and that's all. But then they saw they were at the second week they were starting to do something meaningful, and this is something that is definitely very exciting, you know, coming back and watching improvements. It's so rewarding, and in some sense it's very magical in this domain.
Yeah.
So okay, with Kazumi We are at stage 4 against Lei Fang. This is the 3rd episode. In the second one, we obtain a reward of 4.4, not bad with Raido. Let's see, the average. If the average is somewhere between the 6.5, slightly above, it's not. Let's wait and see. I believe that Kazumi as well as Raido, they were performing very, very good moves, at least let me say intelligent moves. Of course, if compared with the previous week ones, definitely, but also in general, I have a good experience with agent we trained in against the computer, not with self-play, and they are starting, to get good moves, meaningful moves. Now it's totally a different approach. Because against the game, you get familiar with the moves of the game. Here you are playing just against yourself. So and there is also another important difference, because I trained the agent to play against the computer while playing against the computer and using only a single character, so that was Kazumi. And while here, as you can see, we are using all characters available, chosen randomly during training as well during evaluation. And so this is also a very important difference. We are also using all attack buttons combination. That is another one, another important difference, because the action space is way larger, or let me say it's larger for more actions. And so it's good that we are starting to see a meaningful moves here and there, and I believe that this where we arrived today could be a good starting point to restart our agent. Now the choice here today is if we think we should restart training to continue to take a look at self-play also next week, or another thing that we should do soon is take a look at how we are able to train something in a new game, because so far I'm repeating this for at least the second or third time these days. We were able to complete Dead or Alive and Street Fighter, but we do have other 2 games in our already interfaced library, and one of them, the next one, is Tekken. And so that is another option to start training our algorithm on that new game. We'll see. So so far performances are the average should be around 1 point something, I believe, slightly lower than 2, so not impressive, let me say, but definitely something that is better than previous week. So yeah, Zach in this case, we're using Zach. Okay, so stage 1 seems always pretty easy, except that a couple of times we were able to lose at that stage. That's kind of strange usually. Nice here.
Wonder how much deterministic the computer is, when
yes,
this is very important during training. If the computer is very stochastic, it's gonna take a lot more time to train.
I totally agree with you, and this is also something that I've been asking myself, because sometimes it happens that also those I'm wondering, sometimes I wonder if it's like a human impression, or if that's really the case when you, for example, kept playing after you lost. For example, let's say you lost at stage 5. It would be, sometimes it seems way harder to continue from that stage on, instead of restarting from scratch. like if
Really?
the computer, yeah, it seems so sometimes, like if the computer, knowing that you were restarting, basically increased its own power, while when restarting everything, maybe the difficulty of the game could be something like sampled at random when you start the game. The difficulty of the entire run. Sometimes it's kind of strange. I really don't know how they design these kind of things, but it's something that definitely could mess up with our own strategy, and so it's not so easy.
Well, actually, since we have access to the data from the game, we have access also to the actions of the agents, right? So we can actually make two computers play one against the other, and we can try to measure how many times they play certain action in certain moments, and this way also try to determine how deterministic they are.
Yeah, I see your point. That could be very, very interesting. I must say, if you don't have a perfect map of the addresses of your system, in terms of if you want to play to display actions, it's not so super easy to retrieve them. But I see your point, and that could be something really, really interesting to do, to evaluate randomness of determinism of the opponent. It's definitely something that would be really, really useful. Just from what I saw during these months we have been using these games, it happened basically never happened that I noticed some repetition between episodes, standard patterns, except from combos that are there for a reason, but way to approach the match that are basically always the same. I never happened to notice anything similar. So I think there is some stochasticity there somewhere. It should be, I believe.
We should get in touch with the developers of the game.
That would be really, really interesting, of course. Also, get to know how they engineered the
you can invite them.
Yes, that would be super awesome. and yeah, this is I believe this is the 7th episode for this run, so the last one. I believe our performance was is gonna be worse than the agent we had, a 6.5 million in some sense, even though we are not sure this is super meaningful. At least this agent seems to be at least not corrupted as the previous one, and so I believe that we could restart training from here, adding this agent into the list of those one from where to sample, and so see next week how it will perform. That would be very good also, and nice things to watch. So let's see, we are almost there. This is the last run. We are at stage 1. We lost one round. That is usually is not something you should expect with the trained agent. We are almost there, guys. We lost it. So let's see the average. We're gonna see it pretty soon. Okay, this is gonna be stopped. Okay, and so let's see, the average is 1.16. that is bad if compared with respect to the very, very first agent we trained, but I would like to go for another week and then then see if to continue or to move forward to Tekken and leave SelfPlay to our community maybe for a while, or maybe come back to it later. One option would be to start SelfPlay with a partially trained agent, or using imitation learning as a hot start in order to avoid starting from random. That would be another
1.16. It's still at the top of the leaderboard.
Yeah, for now maybe. Yes. Yes, it's not super bad, taking into account that we are using all characters from the option that we can choose. Okay, guys, so yeah, I think that this live was great. We had the chance to talk about a lot of very, very cool stuff. I will definitely, as usual, you find all episodes on our website under episode tab, and on our Twitch channel, of course. I will definitely share highlights of this session next week. I believe on LinkedIn I will share them, because I believe it's very worthwhile for the community to know we talked about this one. I will also put it under our tutorial section that you find in the download part of our website. As you can see here, today's episode was good because I believe it provides, in some sense, guidance for to apply GA on neural networks. That is super interesting. Okay, so very, very great episode today. I want to thank you all for being here. First of all, thank you, Alessio, it was great. Your presentation was great, and thank you, Lorder, for being with us. It's always a pleasure to interact with you guys on the chat. I invite you all to join us also on our Discord server. You can access it from the website, and you will find all of us there. Alessio is there, of course, already sharing a nice amount of very interesting stuff. So, Alessio, again, thank you very much for being with us.
Thank you very much.
It was really, really interesting. Thank you. And thank you all, guys, for being here, for watching. We'll see you next week on Tuesdays, usual, and also Thursday. And for today is all. I wish you all good night. See you next week. Bye-bye.